Let us take a look at an inductive circuit, an RL circuit, and we'll compare it to our capacitive circuit from last topic. The time constant of the capacitive circuit, and actually it's an RC circuit, is 1 second. That would be 1 ohm times 1 farad. And likewise, the time constant of the RL circuit would be 1 second, and that would be L divided by R. 1 Henry divided by 1 ohm is 1 second. So we'll start by taking a look at what happens within the first 5 time constants. So we would be expecting to complete the analysis here at 5 seconds. We can put a 5 in there, and then we'll simulate this. It's calculating a lot of points, so it takes a little while to get out there. And let me make the traces a little bit thicker so we can see them a little better. And let me do this guy here. Oops, missed. There we go. So the red is the capacitor, and as before, when the switch is closed, then the initial value of the capacitor is 0 volts, and that's kind of important to know that, is the capacitor will asymptotically charge toward 10 volts. And when it reaches 5 time constants, which would be here, the industry says that the capacitor, for all practical purposes, is charged. Now the inductor behaves quite differently. When the input voltage from our little generator goes from 0 to 10 volts, small current starts to flow, and that builds up a magnetic field, and that magnetic field cuts the wires of the inductor and induces a counter EMF, that is CEMF, that opposes the current that flows. So basically offers a high, and I'm going to use the word resistance, to the flow of current. Now, as the current is overcome, and it has to be when you think about it, is that the voltage across the inductor now will drop, and it will asymptotically approach 0 volts down here at 5 time constants. Now, this is for an inductor with 0 winding resistance, and that really doesn't exist. So that would be the theoretical point of this. Now, at this point, the capacitor is completely charged and has its energy stored in an electrostatic field. And at this point, the inductor is completely fluxed. That's the word for magnetically charged, and has all of its energy stored in a magnetic field. This is potential energy. You saw me disconnect the capacitor and walk over and connect it to a light bulb. This is kinetic energy. As soon as our source voltage goes to 0, it'll discharge immediately. So in both cases here, the energy stored in both of these is the same. The energy storage in this would be 1/2 CV squared in joules, and the energy stored in the inductor would be 1/2 Li squared in joules. So that's what the charging phase or the fluxing phase would look like for an RC and an RL circuit. Now let's go back and take a look at the next 5 time constants where the input voltage here goes to 0 volts. I'm going to point to that right there a little bit. And keep in mind that this is a perfect voltage source. So when this goes to 0 volts, effectively Vin is connected to ground. The capacitor will discharge in this direction because it was charged being plus on this terminal, and the current flowing through the inductor during the first 5 time constants was in this direction. Now it's the characteristic of the inductor when flux was being built up to oppose the current. Now when the voltage goes to 0, the magnetic field begins to collapse. So the voltage across the inductor is going to be opposite, and what it wants to do is to keep current flowing in the same direction. So think of an inductor like a flywheel in a motor. It doesn't like to change quickly. So let's go up and resimulate this again. And what I'll do is change the stop time from 5 seconds or 5 time constants into 10 seconds so we can see the discharge phase of this also. And we'll get there. All right, starting on the discharge phase. And there were 10 seconds. Let me change the thickness of this for viewing ease. And the Same with the inductor here. So in the case of the capacitor, we've reached 5 time constants. The industry says it's charged. The input voltage goes to 0, and the capacitor starts to discharge through the resistor and through the source, which is 0 ohms, until 5 time constants later, the voltage across the capacitor is virtually 0. Now in the case with the inductor, the charging phase, or the fluxing phase rather, is the same, and at 5 time constants, the voltage across the inductor goes from 0 to negative 10 volts, and that's due to the collapsing of the magnetic field that wants to keep the current flowing in the same direction. So that's why this is negative, and then as the magnetic field collapses, is what we see is the energy and the voltage across the inductor asymptotically approach 0 volts. Now if I were to plot the current in the inductor under these circumstances, it would look exactly the same as the shape of the voltage. Now let's go back and say one more comment about the schematic here. After 5 time constants and the inductor is completely fluxed, the voltage across the inductor, and this is DC voltage, is 0. Therefore, all of the voltages across the 1 ohm resistor, so that would produce a current of 10 amperes. When the capacitor is completely charged, meaning that it's 10 volts, we have a 10 volt rise and a 10 volt again rise, because this would be the plus side here. The current through the capacitor is basically 0, and the voltage drop across the 1 ohm resistor is also 0. So as what you can see here is inductors and capacitors have very, very opposite characteristics as we would expect. So that'll conclude.